Okay, so I'm going to quickly show you an example how I get an overall E0 of cell, electromotive force, or the total voltage from a redox reaction using the net potential tables. I call this the third skill in redox. Okay, first was assigning oxidation numbers, second was writing half reactions and identifying, of course, the agents and who got oxidized and reduced. And the third skill is determining whether the reaction will work or not. And spontaneous, we use in thermodynamics, means we have a directionality. And redox reactions are forward direction reactions, either work or they do not. And we can talk about and discuss and evaluate how well they go forward or work at all based on their voltage. As we've talked about, the voltage is a pathway, potential difference in charge, so that current could flow if this was a battery. But it really demonstrates whether electrons are transferred, okay, and how spontaneous and directionality, if there's a forward movement. And if this is going forward, of course, the reaction is occurring. And we can basically see whether or not this occurs or not, okay, or how spontaneous, what kind of direction do we have. Any case, so in order to do this, we first have to finish out this reaction. This is a single replacement, and we have copper and we have hydrochloric acid, and we're going to see what it makes. Well, this is a 0, this is a positive, and this is a negative. And I'm trying to replace the copper with the hydrogen. Now, for this to work, hydrogen has to go to 0. If it becomes electrically neutral, then it no longer attracts itself to the chlorine. So how's that going to happen? Well, the only way that can happen is if the copper could give the hydrogen some electrons. And if it did that, okay, we'd be very successful. All right, so we're going to guess for this to work, copper has to oxidize. Copper has to become copper plus. Now, you could use copper plus 1 or copper plus 2. I'm going to use copper plus 1 to make things a little different, okay, a little crazy, probably not that crazy. Any case, what I'm going to do here is assume that copper was able to give its electrons to the H plus, okay, and we're going to evaluate whether that was possible in this area here, okay, but we're going to assume for this to go forward, this has to happen. So we're going to assume that does happen. So copper gives electrons to the H plus, hydrogen comes out, okay, and the copper moves in to make copper chloride, let's say, copper plus 1 chloride. Now, in truth, hydrogen's probably going to react with itself to make 2 H's, okay? So we're probably going to need a 2 in front, okay, or a 2 here, okay, if you wanted to do it quite like that. Okay, and of course that'll give me 2 coppers. All right, now we're going to get to balancing a little later with redox reactions, but that's how the reaction would go, very simple. Any case, let's go ahead and go forward. So copper is going to oxidize into copper, in this case, plus 1. I know you could use plus 2, I just chose to do it. I was being told. Okay, and this is plus 1. Now, how did copper go to plus 1? It had to give up an electron, as we showed right here. It's the only way for this to work. H plus would not be replaced by copper unless it became a 0 and no longer attracted, and then copper becomes copper plus 1, and now it's attracted to the chlorine. Okay. Any case, who's getting reduced? Well, the proton becomes an H0, and the best way to write this, it becomes hydrogen and 2 of these, and has to absorb 2 electrons. Now, look very carefully here. If this is absorbing 2 electrons and this is giving off 1, we're kind of unbalanced here. So that's why you would say, well, okay, we would probably put a 2 here. Why? That balances, but putting a 2 here means we have to multiply everything by 2. We have to distribute that 2. And that's where we get the 2's from. So by balancing the electrons, okay, we automatically balance, okay, our entire reaction, all right? 2 H pluses are in 2 HCl's. So that's how that works. So balancing electrons in redox reactions balances the charges and it balances the reaction. So that 2's that we got there could have been identified through the half reactions. And that's a little aside, a little hors d'oeuvre, so to speak. Okay, any case, moving on. So who got reduced? Whose charge went down? H plus went to 0. Now, before I go forward, and I am going a little quick here, to make sure that your half reactions are correct, make sure that both sides of a half reaction have the same charge. Copper plus, copper 0, and overall we have what? 2 plus, okay, and a negative 2 is 0. So that's correctly done. and this is my oxidation half reaction. And of course over here I'm gaining 2 electrons. My charge is going down, and just as a check, -2 and a +2 is 0. This side is 0. The absolute check you must do is making sure that both sides of a half reaction have the same charge. It doesn't matter if this has a different charge. Okay? Eventually we will make sure it has the same charge by balancing electrons. Any case, reduction, half reaction. So substance reduced is H+. Okay, substance oxidized, okay, is copper, at least theoretically, and the oxidizing agent is the one who gets reduced. Think opposite when you hear the agent, and opposite of oxidizing is reduced. Okay, obviously if this one is getting reduced, what's it doing? It's pulling electrons away from the copper, so this is helping the copper get oxidized. For the same reason, the reducing agent, opposite, is the one who gets oxidized. And the copper 0, we're picking always, my friends, from this side of the reaction. We care who is passing it around, not what happens after. Okay, so that's all review. Now, how do I get net potentials? Well, as I talked about in a previous lecture or in class, I talked about the standard cell. Every one of these half reactions was compared to this reaction, or its reverse, to come up with some kind of relative scale of a pathway called voltage. So all we got to do is go to that table, and let's look at, well, H plus 2 electrons plus H2. Well, that's going to be the standard cell. Nope, not that. The standard cell, okay, which would be right here. So there's my standard cell. 0. Okay, so no problems there. That's going to be 0.0. Oops. Why is it 0? Because, well, that's the cell or the half reaction that all of the other net potentials are based upon. So that's the reference point, so to speak. And we're going to do copper now, oxidizing. So I go to my net potential table, and copper oxidizing, okay, does what? Let's go in reverse. Now this is oxidizing to copper +1. So wait a minute, it's a reduction table as written, so oxidation is in the reverse. So this is positive 0.5 as copper +1 gains an electron, but it'll be negative 0.52 as it goes in the reverse. So negative 0.52, all right, negative 0.52, and as you can see, very easy math here, negative 0.52, and essentially what we just did is we attached it to the half cell, and it would of course just be equal to its net potential, but obviously it is not spontaneous, okay, which means copper does not react with hydrochloric acid to make hydrogen. That's an important point, okay, because there are many questions and many people expect you to understand when can you make hydrogen gas. Okay, if you look at my net potential table here, okay, I'll make this a little smaller so we can see some more of this. But if you look at the standard cell in the middle, there it is. Okay, right here, let's just outline it right here. Here's my standard cell. If H plus is going to get reduced and go this way, okay, it can only get reduced by elements that are strong enough what? Strong enough reducing agents. And as you go up in this table, it might be different from when you see in your class if you're different. Okay, in this table, I have the metals listed up top, and they're more negative as you go up because these metals love to oxidize, so their positive values actually get bigger when you consider them going in the reverse, right? This is listed as reduction tables. So only elements, okay, that oxidize are above the ones who reduce. So H plus is a strong enough, okay, oxidizing agent that can make all of these oxidize, or you can do the reverse and say that all of the ones above the H plus are strong enough reducing agents to force H plus to oxidize. All of these elements, when combined with H plus, will give positive values, obviously, because the reverse is this positive 0.4 plus the 0. Look where copper is. Copper is below the H plus. So anything below it means that one of two things, that this reducing agent, okay, the one who gets oxidized, copper, I should say, the reducing agent is not strong enough to force the electrons on the H+. Or this H+ is not a strong enough oxidizing agent to the copper. Okay, and that's the best way that I like to explain it. This H+ is strong enough to force all of these metals to oxidize and produce hydrogen gas. So only these metals above the H2 make the hydrogen gas, whereas you can see that, silver, and if we go down even farther to gold, the unreactive element, who hates to what? Oxidize going in that way, is not going to make, and it makes sense. We use copper pipes or sheathing, okay? It's not a very reactive metal, all right? Any case, that's skill number 2, and that's all you have to do is remember that you do your half reactions, write the half reaction as written, take the value as written because this is a reduction table, it's all written as reduction, find your oxidation, okay? And then, of course, you have to reverse the sign because we're going in the opposite way. And then all we're doing, okay, is adding them together. And that's how we come up with a net standard potential. All right, rock on.